Yay. All right. Welcome to week 10. It is week 10 already, guys. Can you believe that? I can't believe that. It feels like August. No, I'm just kidding. It doesn't feel like August, but it feels like August was a lot closer than it was. But anyway, it's lab 6. We are getting into collisions. Collisions. Anybody have an idea of what we're going to talk about today? Anybody? Type it in chat. Voice it out. Move this chat box. Nobody knows what we're going to talk about? Can anybody think of an example of a collision? Type that in chat. Just give me one example of a collision. Maybe be creative, because I feel like there's a lot of them that are like basic, but we can be creative here. Oh, good one. Yeah. Nobody else? Gosh, you guys are having just the same morning I am. Okay, yeah, so bumping into a car, absolutely. Playing pool, that was so creative. Yes, that's like the perfect example. Playing pool, absolutely. Anybody else? I can think of one. Particles colliding together. That's just because my mindset's in physics all the time, but I'm thinking about particles that are bumping into each other, particularly liquids, gases, especially if there's like boiling water. There's lots of high energy particles. Good. Okay. Yes. We're going to move on. We're going to talk more about it. But first, we're going to review Lab 5 Part 1 because when I was grading, I had a lot of issues with calculating percent difference. Percent difference is very different from percent error and percent change. I had a mixture of these two and then some that I think you made up. I don't know. But whatever the case, this is percent error. Percent error deals with theoretical and expected values, or actual values and theoretical values, something like that. Percent change deals with old values and new values. Still kind of the same, but notice absolute values, absolute values. Percent difference, which is the one I wanted you to calculate, is this formula right here. This one. Notice how the denominator or the numerator is in absolute value. That makes it positive. So any values can be positive. This is what I was looking for. Here's an example of what we're going to talk about today, and this is taking the percent difference. Now, in the lab today, you are not going to take the percent difference. You are going to take percent change. However, this was like a funny, just coincidental example for momentum and collision. But you are going to calculate percent change in this lab coming up. Okay, good. Got through this. Also, request for lab extensions. Guys, the very first day of school, I said, hey, you can have an extension for as how many ever days you need, whatever you request. I don't care if it's 1 week, 2 weeks. I don't care. Let me know. COVID's a weird thing right now. There's a lot of things going on. There's a lot of things that can affect your life that wouldn't have been affected if COVID weren't a thing. So, however, my rule is 60 minutes before 11:59. So if you message me at 10:59 or even 11 o'clock, that's fine. You will be able to then ask me for an extension. However, if it is after that time, I cannot give you an extension. This is a rule that I've had since the very first day of school. I think the one in the syllabus is either the same or it's actually way worse. I say, oh yeah, you don't get any extension. If you don't turn it in at the time, you get failed. Okay, that's not the case here, but just make sure. Now, I did talk to a couple people. I don't think I emailed one person back yet, but if you asked for an extension for like from this weekend, I will give it to you. Even if there was, I know a couple people and I said, no, you cannot. Well, I'm going to give you a grace period. So I will give you those points back. However, from now on, it's not going to happen. You have to ask me for the extension 1 hour before the due date, the due date time. Okay, cool. So yeah, you guys get grace period. So you should be happy, even if I said no. This week, collisions. Collisions have to do with momentum. Does anybody know the equation for momentum right off the top of your head? Or make it up? What do you think the equation for momentum is? Blah, 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 blah. Yes, Monday. Also, this gift right here is an example of momentum.
Is it mass times velocity, since the units are just kilograms times the units per second?
Good job. Good job. Yes. Yes, it is. So I am going to type that in. P equals mv. Now, there's a thing here. There's a thing here that is very important. P, which I will bold, and v, which I will also bold, are vectors. And if you don't know what a vector is, you guys should know what a vector is. But they are vectors. So I'm bolding them out because I can't put an arrow on top of it. But if these letters are bolded, that means it is a vector and there should be like a little arrow on top of it. I guess I can draw it. Let me see. Like that. Yeah, great. And like this. Yeah, that looks awful. Should be like that. Great. So obviously you can figure it out. It's mass times velocity. You have a mass and you have a velocity. Simple. Simple like that. We're going to talk about conservation of momentum, which is technically this. So it's this equation right here. It's a little messy, but if you go in your textbook, it'll look a lot nicer. It'll look a lot neater. But this is the conservation of momentum right here. And it's basically P is momentum. Obviously, momentum is mv. You just plug in mv where the P's are, and this is what it looks like after you plug in that mv. Now, A and B and A and B, this is if you have like two objects, obviously. Oh, by the way, right here, this highlighted thing, if it says F net equals 0, which means like the net forces are equal to 0, that just means that the system is frictionless. So you don't have to worry about calculating friction. There's no coefficient of friction. There's nothing like that, because F net will equal 0 in all of these cases. Cool. Yeah, like I said here, plug in MV. And then as you can see right here, oops, it's a little different. That is because elastic collisions, they conserve the internal, so the internal kinetic energy is conserved. That means that this thing has internal kinetic energy, which means what? Is it sitting still? Is it moving? Is it floating? I don't know. What does it mean? What does kinetic energy mean? Some of you still don't know. I feel. So what is it doing? What does that mean? What do you think internal kinetic energy means?
It means that it has a velocity.
Okay. Yeah. It means there's stuff moving. It may have a velocity, it may have a speed, or it could be accelerating. We won't get into acceleration though. That's a different thing. We're going to focus just on velocity, constant velocity. But yeah, It is internal kinetic energy is the sum of the kinetic energies of the objects in the system. Obviously, if it has kinetic energy, it's moving. Great. I'm going to show you some examples of that coming up. Right here. What do we notice? Can anybody name one thing that you notice about this example right here?
When the objects hit the direction of the vectors changes.
Okay, that's one thing. The arrows change. Good. Anything else? I can name a couple things. No one notices anything.
The two balls are of different sizes, so they might be of different masses.
There you go. Yeah, I mean, yeah. It looks to be like these things, these two balls are obviously different sizes. So maybe that means that they have different masses. Maybe. That's really good. And that's basically what this is telling you. Now we could also say, as like a little asterisk right here, if I were to throw a ping pong ball in an equal sized round rock, what would happen?
The ping pong ball would go flying.
Okay, that's good. That's good. Now, what if I had a really big ping pong ball and a rock this size? What do you think would happen? Type it in chat. What do you think would happen? You have a huge ping pong ball, but about this size rock. Are the masses the same? Are they different? They're obviously larger and smaller than one another. I was talking about collisions. So let's say we roll a rock on the table and we roll this huge thing, this ping pong ball on the table. What do you think will happen? There are 9 people, well, 8 other people in this class right now. I should have 8 different chats going on. Not talking about falling. Not talking about falling. There's nothing falling. Do you see these things? Are these balls falling? We're not talking about gravity. We're not talking about anything about falling.
They're gonna both roll in opposite directions, just like in the picture, but the ping pong will roll further than the rock.
All right. All right. That's one. A bigger collision. Okay, let's see. Depends on, oh, okay. Well, so a ping pong ball is hollow. That's what I'm saying. A ping pong ball is obviously hollow. Even though it's bigger. This rock is solid, but it's this big. Yeah, it's a ping pong ball. It's just a giant ping pong ball. I mean, I guess I assume that people know what ping pong is, or a ping pong ball is. It's like really thin plastic. It's hollow. There's nothing in there. Lauren. Oh no. Who else? Alpha. D. What do you guys think? Okay. Okay, that's good too.
I'm
Yeah.
not really sure.
Hmm?
I'm not really sure.
Okay, that's also an answer. Okay. Yeah, so Lauren actually said a really good thing. She said the heavier one will move less, basically. Okay, the bigger ball will move further. Okay, yeah, and why is that? Why do you think that is? Why do you think the ping pong ball will go so much further, even though it's larger? What is the difference there? You have a rock that's this big, it's solid, but you have a ping pong ball that's this big and it's hollow.
It's mass.
Exactly, it's mass.
Okay.
So it doesn't really matter. Like, we can assume that yes, when we see like diagrams, the size of the ball will most likely have a larger mass, but we also really can't assume that. We have to do calculations to make sure that that is the case. Good. You guys are doing really well, even though it's Monday and it's a dreary day and I needed 2 cups of coffee this morning, which is unusual for me. So this is another example of an elastic collision. These balls, I guess you could just say it's like the old video game from like, I don't know, the 60s, the 70s, like just kind of like that. So watch that a little more, just to really observe what's going on here. What happens when the smaller ball hits the bigger ball? What happens when the little ball hits the bigger ball?
It seems like in both cases, they both speed up a little bit.
Okay. Do they speed up equally?
No, the smaller ball definitely speeds up more.
Okay, cool. So what can we assume about that?
More energy is transferred to the smaller ball.
Okay, but why is that? What can we assume?
It's mass.
Yes, exactly. Good
Is
job.
there?
Very good. Its mass is probably a lot less than the big ball. So usually in 99% of cases, you can assume that a larger object means it has more mass. But I just wanted to like make sure that you guys know that that might not always be the case. Cool. We're going to talk about now inelastic collisions. So we had elastic collisions, 2 things bouncing. If you have a bigger object and a smaller object, depending on mass, the smaller object is probably going to go farther and faster. Great. So now we're going to talk about inelastic equations, which is different, or collisions. Did I say equations? I meant collisions. Oh, by the way, these are also in 1D. These are one-dimensional. We're not going to talk about 2-dimensional because that's not in your lab, and you have the book to read to do that. Yeah. So inelastic collisions is where the internal kinetic energy changes, so it's not conserved. So here's an example, like right here, here's a GIF of this. So one's moving twice as fast and it's also weighing less. So if it's inelastic, what happened? Can you explain that? Can you explain why that is? Just guess, be wrong, right? Just give me a guess. You can type it in or say it out.
So it seems like instead of 2 velocities at the end, there's only 1.
Okay.
So
Okay.
it's like they combine to form 1 single velocity.
Okay. Yeah, that's a good observation.
It's also, oh, sorry. It's also interesting because the block is the 3 kilogram block is moving 8 meters per second, and the other one's moving 4 meters per second, but they don't like combine to go 12 meters per second. They still just go 8.
Ah, that is a very good observation as well. Right. So they're not additive velocities. So take note of that, because you should also notice that when you're doing your equations. So when you're writing out and doing these calculations, you should take note of that. You're not adding, these velocities aren't necessarily added when we're talking about inelastic. Okay, good. We can also say that the internal kinetic energy is 0 after the collision in a perfectly inelastic collision. And as I said right here, this example is a perfectly inelastic collision. Lots of long words. I'm sorry if I screwed them up. This is also a good example. You might want to use this example for your homeworks, your reading, your lab. Notice that this ball is at rest, so this one is not moving, unlike this. And you have this big ball that weighs twice as much come in. So when they do that, they're now stuck together. So that's inelastic. Cool. And this GIF wasn't working, but basically it's just a GIF of this, but faster. I apologize. Okay, cool. So we'll get to the lab. Hopefully this video doesn't go too long today. What? Hi. Okay, sorry. My fiance just walked in from work. All right, so things to know for the lab. Guess what? It is a worksheet this week. It is a literal worksheet. I was lazy this week. I haven't gotten much sleep lately. It's drowsy, dreary. I don't know. I just haven't been like really mentally with it. So it's a worksheet. Dr. Diamond made it. I'm editing it to make it look pretty and changing up the words and stuff. But yeah, so it's lazy. It's going to be probably pretty easy. I'd recommend like printing it out if you have a printer or have access to a printer. I really prefer you to write it out with paper and pencil. Or if you have a tablet and a like tablet pen or pencil or whatever, just write it out. Because muscle memory, motor memory, something like, do you know what I'm talking about? Yeah, writing it out. Yeah, don't type it out. Please don't do that. Write it out. I know we have some geniuses in the class. Please write it out and take a picture of it. Or you can just copy it. You can type, I don't know, just do whatever. Also, we're gonna have true and false questions and discussion questions. You're gonna wanna use your book for those. If you have any questions that the book didn't answer, just text me and I'll help you. No big deal. So we're gonna go ahead and view that right now. So 1 second. Yes, I'm sorry, it also hasn't been posted yet. Just because I'm still editing it, I have not made up any discussion questions yet. So I'm gonna have to like make that up. It'll be posted by tonight for sure. So don't worry about it. I'm going to change it to, okay, here we go. 1 page. Yeah, so it's just like a worksheet. I give you formulas. So you have all of these things that you may need. Also, you can assume that all the masses of the carts are 1 kilogram, unless it states otherwise. And you just fill it out like a worksheet. You do the simulation, which I didn't link here, but I will show you the simulation of it. You're gonna have 2 cars, and it's just like 2 weeks ago, and you're gonna be able to plug in numbers and watch it as a simulation. I really feel like I had a couple people say that really helped them to solidify that knowledge, and that way you can apply it in real life next week, I think. Maybe we're gonna go straight to fluids, I don't know. We still have yet to determine that. But you can also apply this to just in general life, right? So yeah, it's gonna be this. Oh, you have an explosion case. Forgot about that. You're gonna have to answer these questions. Yeah, so I might have to add lines with that. Right here, you want to experiment. I do want to see you experiment with this. If you don't, that's okay. But if you do, brownie points. Experiment with this with different masses. These are the true or false questions. All you have to do is just circle. Circle which one, true or false. I despise true or false questions. Ugh. But if you need help, I'm here. If you have any questions at all about it, if it confuses you, let me know and I can clarify some things. I'd rather do fill in the blank, but because I'm lazy and Dr. Diamond made this up, we'll just say it's okay. Discussion questions, be prepared to answer in a paragraph, maybe 5 sentences. Don't give me like a whole page, just give me like a couple sentences. Yeah. maybe some diagrams. If you want to draw, like if you want to like instead draw and then like label a picture, you could do that too. That would be cool. So we're actually not done yet. We are going to go look at the actual thing. Oh my God. Move. Okay. When you click on the link, which will be in the worksheet, I will also include the link on the lab description page, so that way you don't have to like shift click or whatever the heck you do. You could just go right to that link. So this is the page you'll come to, and you are going to, oh, well, I thought it was bigger. Here it is. Okay, cool. Yeah, so you're gonna get a full screen, hopefully. You don't have to take any pictures, like screenshots. It's a worksheet. You don't have to take any of that. I'm still determining whether I want you to write an actual report, since we're going to do discussion questions. You will have an error analysis section, though. So, yeah. You don't have to do the procedure. I'm not going to make you write the procedure. I'm not going to make you write out the data and observations, because your data and observations are going to be this worksheet. So I don't want you to write out in a paragraph form. Yeah, so anyway, you just play around with this stuff. You can change the values using these arrows like this. You can pick which masses you want. So whenever you go to the explosion case, and it says experiment with different masses to see what happens, you need to do that. Ooh, you know what? Maybe I want you guys to take a screenshot of that. Hold on. Yeah, I'm gonna make you take a screenshot. Sorry, values, cool, all right. I don't wanna forget. ADHD brain, it's a Monday. I'm gonna forget, I gotta write it down. Okay, yeah, change the masses, change them up, see what happens. I want you guys to experiment. It's what physics is all about. It's what science is all about. Experimenting, trying new things, figuring it out if it works or not. You know, you can do that with math too. So this is for the elastic collision. You have a bar or like a little thing down here that says inelastic collision. Let's see what happens here when this works. Let's see what happens. It's so slow. Man, I should have made that higher. Ooh, nice. Also, another thing that you can use to like test out your experiments or whatever is the PhET simulation for collisions, which I will also link. It's not required, but I think I like it a lot better than this one. But because there was a worksheet associated with this one, I just let it go. I'm sorry, guys. I let you down. But I feel like you guys will definitely understand it a lot better, like collisions in general with this. Oh, and right here is the explosion. So whenever you go to the explosion case in your worksheet, it will say explosion. You need to make sure this is highlighted. Explosion. I repeat, explosion case will be bolded. Don't miss it. Don't forget to put that highlighted there. Does that make sense? Yeah, you're gonna see a little bomb right here. That's the explosion case. Don't forget that. And yeah. So that's it. How do I get out of here? F11? Oh crap. Okay, we're good now. Yeah, so your book's gonna have a ton of stuff to help you out, especially for the true and false and discussion questions. Other than that, that is it. That's it. If you guys have any questions, ask them now. No questions?
What would the error analysis might look like, considering it gives us like exact values for everything in the simulation?
You have to calculate percent change. So I do want you to say, oh, this percent change was this. Why is the percent change that? You can explain other things like hey, how do we know this is exact? I don't know. It honestly just 2 sentences for that. It's gonna be fine. I just do want to see that to make sure. Actually, maybe I won't even include it. I'll see. By tonight, I will give you a thorough list of what I want in the lab description. And obviously, I will attach this Word document, which actually, let's go back to that. So that way, if you guys have any questions, you can see it. Okay. Yeah. So I will attach this as an attachment to the lab description. So you're gonna have to open this as a separate file, fill it out, print it out, fill it out, and then scan it to your printer or do whatever. Screenshot, I don't know. Put it back in and submit it. If you want to print it out, write down all the things, and then go back to your computer and type them out to make them pretty, you can do that. If you do that, see right here, this bothers me to no end, and I don't know why, it just does. If you go like this, or like here, let's put in numbers. If you go like this, and things go like all wonky like this, don't do that. Stop doing that. Just don't do that. What you can do is you can just erase it, like erase the line and just put in the number, like 58,000 million, and then underline it. It's Control U is underline. Make it look pretty. Come on.
So for this whole lab, we will be completing the simulations in physics classroom
Yes.
to answer all these questions.
Yes.
Okay.
Yes, indeed. And there will be a link on here too, but I will link that in the description as well. So don't worry about that. Also, I will also link the PhET simulation as well if you want to play around with that. I had a lot of fun doing that over the weekend, but I didn't really like any of the pre-done worksheets with it. So I really wanted to make my own, but because it was just an exhausting weekend, I just didn't get the chance to do it. So, but Dr. Diamonds is a good second. Anything else? Any questions at all? No questions? If
Oh,
not, oh yeah.
For the explosion case, are we doing one where it's like both masses are 1 kilogram, and then a second case where it's a different, or are we just doing like when they're different masses?
It will tell you in the,
Oh, okay.
literally, like it's a worksheet. It will go through it. As I said before, assume that all the masses are 1 kilogram unless it tells you explicitly.
Okay.
If it tells you explicitly, like right here is the only place, I think,
Yeah.
that is when you change your masses. And even then, you still, for this part, you want to assume that it's 1 kilogram. And then you're going to re-experiment with different masses once you get down here, after you do it with the initial case. Make sense? Okay, cool. If you don't have any questions, you can go ahead and have a great Monday and have a great rest of the week. If not, stick around and ask me questions. Also, Friday night, 4:30 to 7 p.m., I will be doing office hours. If you want to come by at 6 o'clock, if you want to come by at 5 o'clock, if you want to come by at 6:59, go ahead. I'm still here. And we can go as long as, like, I will help you to however long it takes for you to get help. No big deal. I know you guys have work. I know you guys have busy lives, maybe kids, siblings. It's no big deal.
All right. Bye, guys. Have a